All right, welcome back, ladies and gentlemen, to what is our final section of Chapter 5, dealing with exponential and logarithmic models this time. We just dealt with equations, which means we were solving, and that's essentially what we're doing now. We're just going to be looking at more real-world uses of these particular equations and solving differently than what we solved for before. So some of the ones that we dealt with before were things like bank accounts. So you're going to have to remember your A-PERT equation and your other one, depending on the different type of compounding. All right, so we're going to get to that in a few minutes, but kind of bear with us here. All right, so first of all, there are a few different types of equations that are going to be used here. And the first two are your exponential growth and decay models. So both of them look like this. I'm sorry, let's get a pen going here. Both of them look like this, where I get y equals a times b to the x. For a growth, this is just b bigger than 0, and for a decay, this is b less than 0. Or sorry, not less than 0. What am I thinking? That's goofball. That's a goof. All right, b is actually between. All right, I gotta scratch myself out here because I was not paying attention to myself. All right, let's try that again. Exponential growth is when b is bigger than 1, and decay is when b is less than 1 but bigger than 0. We don't like any negatives. All right, so b has to be also bigger than 0. Now, the thing is, when we're calculating b, you're going to be usually given some sort of rate. So this is actually going to be calculated by a times 1 plus b, or not b, r, because we're going to use rate. 1 plus your rate to the x power. Now, if your rate is, if you're increasing, then it's going to be a plus, so it's bigger than 1. If you're decreasing, you're going to subtract your r, so it's smaller than 1. You'll see what I mean here in a few minutes, looking at a couple little examples. All right, the next one is what's called a Gaussian model. In this particular one, we're not going to be dealing with a whole lot, but I figured I might as well just show you what it looks like. I'm going to get rid of that there. And a Gaussian model looks like y equals a times e to the power of negative x minus b squared over c. So nice big ugly exponent. These can be used in real-world applications. I don't know all of them off the top of my head, but you could probably look them up in the textbook here. The next one is a logistic model, and if you're a biology person, you've dealt with this formula before. Logistic model looks like this. Y equals a over 1 plus BE, oops, sorry, not E. Oh, yeah, it is. Sorry. E to the negative R X. R is rate, E is E, your Euler's number. A and B are usually given to you. All right. And the last one here is the logarithmic model. This is another one we're not going to be solving a whole lot of. We actually just solved a lot of these in our last section, but y equals a plus b ln of x, or y equals a plus b log base 10 of x. So these are our logarithmic models depending on the situation. All right, so that's really just the different types of equations we're dealing with. Let's take a look at what we're actually doing here. First of all, next couple pages here are just going to be interest equations. So whenever you see, and this is what I really stressed the other day, the word continuously means a PERT. I guess we used a capital P the other day, didn't we? A PERT. A is the amount you have in your account afterwards. P represents principal, or the amount you invest. R is your rate, and T is time. And this really is an exponential growth model. If you're putting money into a bank, I hope you're making money. So here's an example. You invest $1,000. Your annual percentage rate is 12%. It's compounding continuously. That's what this page is about. And I could ask a couple questions. One, how long will it take to double? All right, so, well, that's pretty easy. This is actually the easiest of the 4 questions I ask here. So, how long will it double? I know, okay, well, P is the amount I invest. My rate is 0.12 T. And I want to know when is it going to double, so that means I need to know I have $2,000. So I divide by 1,000, I get 2 equals e to the 0.12 t. Well, we just learned in order to get rid of exponential, we take, or base e, we take the natural log of both sides to cancel the e. And now I can just say t is natural log of 2 divided by 0.12, which is approximately, if I pull out my handy calculator, ln of 2 divided by 0.12, 5.78 years. Now, the other side of this question is actually the really easy one. How much money do you have after 10 years? Well, it's how much money do you have? So that's your A, equals 1,000 times e to the 0.12 times 10. This is the easy one. You don't even have to do anything. You just plug that in your calculator. 1,000 e to the 1.2 power. And after 10 years, you're going to have 33.20. And, oops, sorry, and 12 cents. And that kind of makes sense. If it took a little more than 5 years to double, it should probably take close to 10 years to triple, right? Ish. All right, let's look at another example given different information. Now your initial investment is $500, and you have $1,505 after 10 years. There's a couple questions we need to ask. What was your annual percentage rate, and how long does it take to double? That's 2 different questions, by the way. So, what is your annual percentage rate? Well, we're going to set up the equation exactly as before. So, you have $1,505, and you initially put in 500. E to the power of r, I don't know r, times 10. And you notice this actually looks a lot like the very first problem we did. Only in this case, instead of solving for t, we're solving for r. So we're going to do the same thing here. 1,505 divided by 500 equals e to the 10r. Take the natural log of both sides. And divide by 10. So r is approximately, if I do that really quick, ln of 1,505 divided by 500 divided by 10, 0.1102. So r as a decimal is that, r as a percent is 11.02%. Don't forget to move your decimal twice. And now that you know r, you could actually figure out how long it would take to double. Notice you couldn't answer this question first, right? So you needed to figure out your rate first. So here I go. It's going to double, so that means I get out 1,000. I plug in $500. E to the r t. I'm not going to plug in 0.1102 because I want to use that exact value by using my ANS button as before. So I'm going to divide by 500. I'm going to get 2 equals e to the RT. I'm going to take the natural log of both sides. And I'm going to say t is actually natural log of 2 divided by r. And because you just solved for r is still in your calculator. So it should be the last thing you did on your calculator. You can just say ln of 2 divided by answer, and it gets me approximately 6.29 years. Right? So remember this little r here. As long as you haven't done anything in your calculator, r is still your answer from your previous question. All right, we'll see what we got here for this next problem. Your annual rate is 4.5. You have in your account $10,000 after 10 years, and I want to know what's my initial investment. All right, so it's still APERT. So I have $10,000. I don't know how much I put in, times e to the 0.045 times 10. So notice I just plugged in into APERT everything I knew. There's 1, 2, 3, 4 variables. E is not a variable. So there's 4 variables. You need to know 3 of them in order to solve for the 4th. Basic math right there. All right, so now the hard question is how I'm going to do this. Well, this right here, this e to this exponent, that's just a number. That means it's a number times p. Well, that means I can just divide. So I'm going to say it's 10,000 divided by e to the 0.45. Multiplying by 10 just moves the decimal. And that is approximately e to the 0.45. That means I initially put into my account $6,376.28. All right. How long will it take to double? Now here's the interesting thing. If I put in P dollars into my account, if it doubled, that just means it's 2 times my initial. It doesn't even matter what my initial amount was. You might have noticed that on the last couple questions when I said how long does it take to double, I eventually just divided by P anyway, and I was left with 2 equals your e to the RT. Well, now I take the natural log of both sides and divide by 0.045. I get t is approximately 15 years. 15.4 years. Which should make sense because it took 10 years to not quite double, so it should take 15 years to get up to double. All right, one more in this same kind of problem here. Initial investment is $750. It takes 7.75 years to double, and notice that the first question, what's your annual percentage rate? So again, just start with what you know. A equals PE to the RT. Initial investment is $750. E to the R, I don't know R, and I know my T is 7.75, and I know I want to double, so double of 750 is 1,500, so I divide by 750, which you could have just started with this if you were clever. Take the natural log of both sides, divide by 7.75, ln of 2 divided by 7.75. My R is 0.089, or in other words, 8.9. Oops, I don't know where the 1 came from. 8.9%. And then we can go on to answer once we know my rate. And again, because this is already in your calculator, I'm not going to write it down, because it's a really long decimal. So I'm going to say, okay, how much do you have after 10 years? So A equals 750, that's how much you put in. E to the R times 10. Again, R is your ANS button on your calculator because you haven't done anything yet. And this is just a number, so all I have to do is plug it in. So as before, just 750 times e to the 10 times answer, I get $1,834.37. All right, these problems aren't too challenging as long as you remember your A per equation. But let's move on to something that's not A per. So by the time you retire, you want $500,000 in your account. You're given a rate of 7.5% over 20 years compounded monthly, and you want to know how much money should you put into that account. How much money do you need to put into the account at the beginning in order to make this a realistic goal? So you got to remember A equals P times, not ERT because it's not continuous. It's 1 plus R over N to the NT. You got to remember that N represents the number of times it's compounded per year. R is your rate, T is your time. So in this case, this particular problem, R is equal to 0.075. T is equal to 20. P is equal to, I have no idea. A is equal to 500,000. And you're in, because we're compounding monthly, that's 12. And we're just going to solve for P. And you'll notice these look a lot like the problems we just solved in 5.4. That's why these are mostly examples today, because we've just dealt with these. So A is 500,000 equals P times 1 plus 0.75 over 12 to the, let's see, N was 12 times T, which is 20. And now in this particular case, this one's not too challenging because you're just solving for P, and this is P times a number. So in order to do that, just divide both sides. Now, sometimes you might have to do a logarithm. Let's say you were given the number here for A and given a P value, but you weren't given the R value. Or you weren't given the T value, I mean. And you want to know how long it would take. So you might have to solve using a logarithm here. Just like we took the natural log before, you can take, and we did a problem just like this in the homework where you're taking the log base 1 plus blah, 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 all of this. All right, so back to this, 500,000 divided by this ugly thing that you better be careful of when you plug it in your calculator. So let me write that out. 500,000 divided by parentheses. Let's just do one more to be safe. 1 plus 0.075 divided by 12, parentheses, caret. Let's just do 12 times 20, which is 240. And then close parentheses again. And this should get us, let's go here. Now I got to type it in. You needed to put into your bank account $187.09. All right, so not too challenging on that problem either, I don't think. Nothing we can't do. All right, these ones, this is kind of cool problems here. This is very real world. You've heard of nuclear anything. Uranium, plutonium, that sort of stuff. They have this thing called half-lives, which means after a certain amount of time, half of that material has now gone away or is decayed, all right? And the word decay is very key. It's an exponential decay model where R is 50%. So I would look like this. It would be, okay, my initial amount times 1 minus 0.5 to the T. And over your half-life, by the way, T over H. So it would just be A, your initial amount, times 1/2 to the power of T over H. So we're looking at 1 year. Now, half-lives are usually very large. In the example I have, the half-life of this material is 1,620 years. Now, some half-lives are like 30,000 years, that sort of idea. So you're given an initial amount of 10 grams, and I want to know how much you have after 1,000 years. So half-lives are really easy. You just say, okay, what was my initial amount? It was 10 times 1/2 to the t over h. So time in this case was 1,000 out of 1,620. And this should make sense because you're not, well, the answer should make sense. Let's get the answer first, and I'll explain what I was going to say there. 0.5 to the power of 1,000 divided by 1620. I get an answer of approximately 6.52 grams. And this should make sense because a half-life is 1,620, which means in that amount of time we would be down to 5. But we didn't quite reach 1,600, which means we shouldn't quite reach 5. All right, what if I asked you a slightly different question, though? Be helpful if that would stop doing that. If I asked you a slightly different question where there's your half-life, and I gave you this many grams. You have this many grams after 1,000 years, and you want to know your initial. So you have 1.5. You don't know your initial, times 1/2 to the power of 1,000 over 1620. So again, this is just a times a number, so I can divide both sides. I say 1.5 divided by 0.5 to the power of 1,000 divided by 1620. And I get, you originally had 2.3 grams. All right, last problem here. I'm going to kind of leave this one to you guys after I give you guys the equation here. You're going to be given a logistic model that you need to solve for K. And a logistic model we looked at before. So let's say I gave you this model that said S equals 500,000 over 1 plus 0.6 e to the kt. And I told you you have 400,000. When t is 3. And you need to solve for k. Well, this requires some cross multiplication. And if I multiply here, this distributes, so I get 400,000 times 0.6. Which is 240,000. Sorry, I ran out of room here, times e to the 3k. So I'm going to subtract 400,000, so I get 100,000. I'm going to divide by 240,000. And I'm going to get what ends up being, I guess, 10 over 12 equals e to the 3k. I just get to take the natural log of both sides. I kind of like this fraction 5/6, by the way. Oops, sorry, that was 10 over 24. That's my fault. Gosh darn it. Pay attention, Mr. Nelson. 10 over 24, which is actually 5 over 12. All right, I'm going to take the natural log of both sides and divide by 3. So you take the natural log of 5 divided by 12, divide by 3. I get k is equal to negative 0.29. And there you go. All right, this wraps us up for chapter 5. Come ready to go, and we will see where we end up. All right, see you guys later.